Yeah, I think that works. Okay, yeah, sorry about that. So, yeah, the first question is about whether a given integer is necessarily a quadratic residue modulo infinite many primes. And I think this is quite well known. So is this familiar to you guys? Does anyone know a proof or a answer to this question?
Yeah, there is a proof using quadratic reciprocity law.
Yeah, okay. Okay, good. So in a bit similar manner, you can actually answer the following variants of the question.
What is quadratic reciprocity law? I don't know that.
Yeah, we'll cover it in a bit more detail later on.
Like
So,
right now you are giving motivation how to use it and something.
excuse me?
Right now you are giving like motivation how to use it.
Sorry, I can't hear very well.
What are you telling right now then? Like
So I'll first give you a hint of what we'll be covering today. So the actual
okay,
proofs
yeah,
will follow.
Yeah, got it.
Then we'll move on from the first two questions to some multivariate variants of the question. So we take any given n integers and wonder if there are infinite many primes such that all of the integers are simultaneously quadratic residues modulo p. And of course we have the following variant as well. Okay. And this is, well, the quadratic part of the talk. And then we'll ask the corresponding questions for general power residues. So question 5 is a variant of question one for gate powers. And of course, in the current form, the question is trivial because we know that if, say, p is 2 modulo 3, then any integer is a cube modulo p. So,
Why is this true? You have what you have written.
excuse me?
Why is this line true?
Sorry, I'm having a bit of problem with the sounds.
Oh, is the sound fine now?
It's okay. So go on.
Why is this true? Then any integer is a cube modulo p.
Oh, well, it's not trivial, but it's quite well known. So idea.
Oh, P is a prime here.
Yeah, P is a prime.
Okay.
Yeah, and the result is actually not true in general because we have some multiplicativity in the structure. So yeah. So that's why we are the condition P is congruent to 1 modulo K. So that this question is actually non-trivial. Okay. And then of course we have again similar variants as in the quadratic case.
So we will be proving all these 8 today.
Excuse me again.
So like we will be proving all of these things today.
I'll be well, I can't give detailed proofs because they're a bit difficult, but I'll try to give some satisfactory answers. Okay.
Yes.
Okay, so these are basically the questions I'll be covering here today. And of course, it would be nice to have some understanding of these questions instead of like yes and no answers to each of them. So yeah, but we'll see what goes on a bit later. So we'll first cover the quadratic problems. So this might be familiar to some of you guys, at least question 1 was, but I hope that at least something like question 4 is not so familiar to all of you. So I'll be covering all of these questions anyways. This will probably take the first half of this talk. Okay. So there was one way to prove this by quadratic reciprocity, as was mentioned by a member of the audience. Does anyone know any easier way? No? Okay. Well, there really are 2 ways to do this. The easy way is as follows. We just apply Hül's theorem to the polynomial x squared minus a. Okay, yeah.
Okay.
But there is the hard way. So the hard way is we are quadratic reciprocity and Dirichlet's theorem. And I'll be giving a bit of details here because this will be important in questions 2, 3, and 4.
Oh,
So-
will you be sharing this overlay file after the class in Discord?
Excuse me?
Will you be sharing this overlay file after class in
Yeah.
Discord?
Yeah.
Okay, thanks.
Okay, so for the details, first of all, because we'll be choosing P to be one modulo 4, we have that -1 is a quadratic residue modulo P, and so by the multiplicativity of the Legendre symbol, it doesn't matter if A is positive or negative. So we may assume that A is positive. Okay, so I'll be denoting the symbol with these brackets. I think this is quite standard. Okay, then we write we kind of take the square free part of A out. Well, this is not precisely the square free part, but yeah, we take the largest squared divisor of A out in the factor B, because that doesn't affect the value of the Legendre symbol. So we have and then we use multiplicativity. I should have written a macro for the symbols, but here we go. Okay, and then we use the reciprocity law. So recall that
I think you should have taken P congruent to 8 mod A, like modulo, like P congruent to 1 mod 8A, because we also want 2 to cancel. Like we also want 2 to cancel because 1 is not always a quadratic residue modulo 2. Like for P congruent to 1 mod 4.
well,
2
so
is
is
not
the
always a quadratic residue.
excuse me?
I guess we should take P congruent to 1 mod 8A.
But if A is even, then P is actually congruent to 1 modulo 8, because by that choice we made.
Oh yeah.
So yeah, it works out. So the reciprocity law says that we can swap the symbol except if both of the primes are 3 modulo 4. And as was mentioned, the law doesn't work if P or Q is equal to 2. So we assume for now that A is odd, but we'll cover the case A is even a bit later in the end. It's not very definite. So because we made the choice that P is 1 modulo 4, we can swap the signs, the symbols, and we do not have any sign issues, as would be the case if we have 2 primes which are 3 modulo 4. Okay, and by the choice of P, all of these symbols are 1. And that's it. And if A is even, then we note in this case, P is equal to 1 modulo 4, and by some results on quadratic residues, then 2 is a square modulo P, and in this case, we're fine as well. Okay, any questions? Okay, yeah, and one comment. Well, no, never mind. So the easy way doesn't really give us anything stronger. One could apply the Skur's theorem to the polynomial x to the k minus a, and then get some answer to question 5, but we can't guarantee the condition that p is equal to 1 modulo k. So Skur's theorem is quite limited when we think of the questions mentioned here. But okay, let's move on. Question 2. So now we want to prove that for infinite many primes P, A is not a quadratic residue modulo P. But of course this fails if A is a square modulo P. Is the square of some integer. But now the question is this the only case? And the answer is yes. I like to phrase this kind of results as a local global principle. So basically what question 2 boils down to is showing that if A is locally always a square, then A is globally a square as well. This doesn't really help us with proving the result, but well, I like to think of the results this way because local global phenomena arise quite often in number theory.
So I think you can choose the largest number cases that for all p greater than k, A is not a quadratic residue modulo p, and then try to get some contradiction using this idea.
Yeah. Yeah, so for the solution, we first assume that A is positive and odd, just for simplicity. The other cases are not more difficult, it's just laborers to work them out, so we'll check this case and leave the others as an exercise. So we can take the largest square divisor of A out. And again, we choose B equal to 1 modulo 4. And as above, we use the multiplicativity of the symbol, and then we use the reciprocity law. Okay. And now we make some choices. First of all, we'll choose P to be a non-square modulo Q1 and P to be a square modulo all the other prime divisors of A. And this choice is possible because, well, first of all, Q1 is odd because A is odd by assumption. And hence we have some non-square modulo Q1. And then we can combine these conditions by the Chinese remainder theorem. And then we just use Dirichlet's theorem.
Do you know any proof which avoids this theorem?
I'll be not proving that today, so we'll take that for granted. And that's it. And as I mentioned, the cases where A is negative or even or both are similar. Basically, if A is even, we can't use the reciprocity law, but we still have the choice to make. So but here the choice is made modulo 8. So we have decided that P is 1 modulo 4 to apply the reciprocity law in an easy way. So then when we think of the symbol 2 over P, then we should decide whether we take P equal to 1 modulo 8 or 5 modulo 8. And his choice then decides the sign of the value of this symbol. So that's actually quite similar to the above. The case where A is negative is a bit more laborious because we can't necessarily take P equal to 1 modulo 4. say if a is equal to -1, for example. But this is basically the only case where we can't do this. So, yeah. Okay, and that's it. So if we take b equal to 1 modulo 4, it doesn't matter if a is positive or negative, as we already noted in question 1. So that's basically it.
What do we do for a equal to -1?
Well, then we just take b equal to 3 modulo 4.
Okay.
And yeah, in general, if a is minus 1 times a square number, then we have to take b equal to 3 modulo 4. But that's the only case. And otherwise, we can use the proof I gave here. I also mentioned that by working harder and by using the equidistribution version of Dirichlet's theorem, one can actually determine the density of primes p for which A is a square modulo p. And that turns out to be 50%, which is probably not very surprising because we know that half of the integers are quadratic residues modulo prime and half of them are not. So yeah, that's what you could expect the density to be.
What is equidistribution version of Dirichlet?
So the version says that so it basically says that the outcomes are the values of p modulo m are random in a sense. So they are not biased to any given residue modulo m. But yeah, I'll be not covering this in detail. You can take that as an exercise if you want. Okay, then for the question 3. That's actually very easy with the machinery we have given above. So we just take p equal to 1 modulo some suitable number, and that's it. The fact that this works follows by the claim in question 1 when we assert that p equal to 1 modulo 4a works. And yeah, that's it. And of course, we again need Dirichlet's theorem. But as some of you might know, the case when we have 1 modulo something is actually quite easy to prove by using cyclotomic polynomials. So in this particular case, we don't need any analytic number theory or anything, just an elementary argument using cyclotomic polynomials and Zur's theorem. And then for the final question on quadratic residues. So we have some given integers, and we want that all of them are simultaneously quadratic non-residues modulo p. And obviously this isn't possible for any AI. But there are actually some other cases where this fails as well. Consider the case when we have the integers 2, 3, and 6. I claim that these can't all be simultaneously quadratic non-residues. So the proof is quite easy, which is just need the multiplicative of the Legendre symbol. And that's it. So this generalizes to proving that if there is some odd number of the integers AI having product equal to square number, then the answer is no.
In other cases, is the answer yes?
Yes. And okay, then for the proof. I will make some simplifying assumptions, which are not very serious, but you might not like it. So you can check the other cases if you want. But so yeah, I assume that the integers are positive. And well, that's interesting on its own. So I hope this is not too bad of an assumption to make. And this is as well the only assumption I will make. But if you want to cover the negative case as well, then that needs a bit more work. But I'll sketch that case too. later on. Okay. The main idea is, well, to first use the ideas we gave earlier on. So okay, so we can use the idea we gave earlier on. But there is note that we have a lot of choices to make. And the question is, how do we choose? Well, first we have to note that we're given some conditions, namely that a given integer AI is a non-residue modulo P. Which translates to that for a given subset of primes Qi, an odd number of them should be quadratic non-residues modulo P. Okay, so the idea is that we can think of this as a system of linear equations modulo 2. And that's the main idea. So we have some type of equations of form. The sum of these variables should be 1 modulo 2. So here xi is 1 if we pick qi to be a quadratic non-residue modulo P, and 0 if we take qi to be a square modulo P. Okay, and now the question is, when is such a system solvable? Well, obviously they aren't solvable always. For example, if we have the system of form x1, x2, and x1 plus x2 are all 1 modulo 2, then obviously we don't have a solution. The general case is that we have a solution. We don't have a solution if we can take an odd number of our equations and sum them up to get a contradiction. So in this case, we take all of the equations, sum them up, and the left-hand side is 2 times x1 plus 2 times x2, which is of course 0 modulo 2, but the right-hand side is 1 modulo 2. And that's a contradiction. And then using some linear algebra, you can show that this is the only case where the system is not solvable. This is not obvious, but the proof idea is quite simple. So if we have some linearly dependent equations, then we either get a contradiction like here, or we can just drop some of the equations without affecting the solution set. And then in the independent case, we have a solution. And when we go back to the original problem,
Why do we have a solution when the equations are linearly independent?
well, that's a linear algebra fact, which I will not cover here, but that's a general principle in linear algebra that if we have some independent equations, then the system is solvable.
Okay.
It's not directly, it's not really by definition, but it's not very far from that either. So but yeah. And note now if we have some equations, an odd number of equations, which by summing up we get a contradiction, and this means that the product of some of our original numbers was the square of an integer.
How?
It's basically by definition. So yeah, it's basically by definition. So we have some notation here which we have to undo, but for example, the case where we had 2, 3, and 6, the motivating example around here, that corresponds to the equation, system of equations we have here. So you can think of x1 corresponding to the prime 2 and x2 to the prime 3. Okay, so then the system, the equations of form sum of xi is 1 modulo 2. This basically tells that we have some integer ai for which, when we have taken the largest square divisor of a out, then the prime factorization of a contains those primes and those primes only. And then it drops from there. Is that clear or?
Clear.
Yeah, okay. But you can think of that by yourself after the lecture if you want. So I'll be giving the overlay file after the lecture.
Like seeing the output.
Okay, and I'm gonna comment on the different cases we have omitted here. But yeah, okay, the case where one of where we also have even integer, even integers is not different, because then we again have a choice to make for the prime 2. Either we pick p equal to 1 modulo 8 or 5 modulo 8. And also if we have some negative integers, then we might pick p equal to 3 modulo 4. So we have one more choice. This is a bit more difficult because the choice we make here affects the choice we have to make regarding the primes qi for qi equal to 3 modulo 4 or qi equal to 2. But the main idea is the same. We have some choices to make, and we have to make the choices so that a system of linear equations modulo 2 is solvable. Sorry, is satisfied. And yeah. Okay. So that's about the first half of the talk. So let's take a 10-minute break and continue at 1/2 Sorry, it's not 1/2 to you because of time zones, but we'll continue in 9 minutes. If you have any questions, feel free to ask.
Shouldn't the density be 1 by 3, half into 2 by 3?
Sorry.
Shouldn't the density be 1 by 3, half into 2 by 3? Like,
I mean, the idea here is that 2 is a quadratic residue modulo P half of the time, and 3 is also a square modulo P half of the time. And one could think that these are, in some sense, independent of each other. So that gives you 1/2 times 1/2, which is 1/4.
okay. And why are they sort of independent?
That's not obvious at all. I hope it's intuitive to you, but it's not obvious. But basically one has to do the same argument we have done here. So we note that we have different choices to make. And then one thinks that, okay, the linear equations we obtain for the prime 2 and prime 3, they do not have any common variables. So it follows from there.
Okay. Actually, basically, whether 2 is not a quadratic residue depends on modulo 8, and of 3 depends on modulo 12.
Yeah.
But their like LCM is 24, so I think some factor of 1 by 24 will be kind of intersecting.
Well, we can check this case by hand. So let me think for a second.
Five and 7, I guess. Modulo
Yeah.
12.
No, that's not right.
So is there any rigorous way to generalize this?
Sorry?
Is there any rigorous way to generalize this?
I mean, Dirichlet's theorem is usually thought to mean that we have infinitely many primes P such that P is equal to 7 modulo 24 or something like that. But
No, like
Yeah.
how to prove that they will be like they would not depend on each other. They are kind of independent.
well, in this case, we have proven this already because, I mean, in this proof here, I didn't say anything about them being independent. I just used the Chinese remainder theorem and so on. And in the general case, well, I mean, you can't think of the independence being anything like formal or any formal argument. It's just some heuristic idea of what to expect. And of course, they aren't always independent. for example, if you have 2 and say 18, which is 2 times 3 squared, then of course the conditions are not independent. Or another case, 2, 3, 6. So you have to be a bit careful by what you actually mean by the independence. But in some sense, these are obvious cases. Like, of course, 2, 3, and 6 are not independent of each other because 2 and 3 determine 6. But if there is no trivial abstraction, then you can think of the conditions being independent of each other. And you can prove the independence result by a modified version of this argument we gave here. But that requires a bit more work. If you want like a formal way, like a formal definition for the independence, actually what I mean is that the system of linear equations we get, in that system the equations are linearly independent.
Yeah.
And that in turn is equivalent with the fact that the product of any of the given integers shouldn't be the square of an integer.
I didn't get the last part you said about the equations. How are you relating all this stuff with those equations thing?
So this is what I mean by independence. No subset of the given integers should have a product equal to a square number. So if this condition is met, then the densities behave exactly like you would expect. Okay. Is this clear?
I didn't
Yeah, the thing you have
understood
written
this
is
one
fine.
part too.
Sorry?
I didn't understood this density part. How you got the density?
Well, yeah, let's say that's an exercise, but I
Okay.
assume the result is clear, what I'm trying to say. Okay. Okay, well, I guess we'll then move on to the higher power residues. Well, first of all, I would like to say there are no surprising results coming on here, except, well, yeah, maybe one thing, but in some sense, the independence ideas carry on to the higher power residues. So we take a third example of thinking whether 2 is a cube modulo p or not. And of course, we have to restrict to p being equal to 1 modulo 3, because otherwise the answer is trivial yes. A heuristic would be that for these primes p, 2 is a cube modulo p, roughly one out of 3 primes p, simply because 1/3 of the residues modulo p are cubes. And one could think that 2 is not an especially likely or unlikely number to be a cube modulo p. Okay. These questions are unfortunately quite difficult. For example, I do not know of any elementary proof of the fact that 2 is not a cube modulo p for infinitely many primes p. If you know of any, then please let me know. But yeah, that's a difficult question. The case where we ask that 2 is a cube modulo p, for that we have an elementary proof.
So like we have these nice properties with quadratic residues that we have this multiplicativity and reciprocity law. So do we have similar things for cubics also?
Well, the problem is that the higher power reciprocity laws are quite horrible to use. I mean, well, first of all, you have to think of some field extensions of the rational numbers and then consider what happens over there. But you can't really like, you can't give a similar argument. I mean, no longer the conditions correspond to Congress conditions on P. It's, I mean, this is some kind of folklore result that, of course, you can't expect this to hold. But I can actually, I mean, you can give a formal proof of this result. So you can prove that this condition 2 is a cube modulo P is not determined by Congress conditions on P. So that immediately rules out a lot of different proof methods we have used in the quadratic case. And of course, you could think that the proofs I have given on the quadratic cases are not very elementary either, because I have used Dirichlet's theorem. And I mean, that's true. But there is a proof of this result that 2 is a cube modulo infinity many times p congruent to 1 modulo 3. There is a proof of that result not using Dirichlet's theorem. So only using Schur's theorem and some elementary arguments. But yeah, okay. To get back on what I'm going to talk about. The heuristics are quite good. So, for example, the heuristic I have given here that 2 is a cube modulo p roughly 1/3 of the time. That's correct. So you can prove using some heavy tools that this is actually the case. So in some sense, there should be nothing surprising going on. And that's the main idea I'm trying to explain here. And if you don't believe in me, you can just do some check by computer. So you go through all the primes and check if the equation is solvable or not. And then you see that, okay, it seems to be about 1/3 of the time when the equation is solvable.
Like, do we have to do some coding or what we have to do?
Yeah, you should do some coding. Of course, you can check it by hand too, but that's a bit slow.
Okay.
Okay, and I would like to give a general result regarding this fact. Okay. First of all, I'm going to I need a generalization of the Legendre symbol for the empty powers. So we of course consider premise p equal to 1 modulo m. And we note that how do I put this? So we define the mth roots of unity modulo P just by taking the solutions to the equation next to them is 1 modulo P. So we know that there are m non-congruent solutions by the condition P equals 1 modulo m. For a proof, just take a primitive root modulo P
I
and
didn't get the claim you are making. They are the thing you are making.
excuse me?
I didn't get the. Can you repeat what is the claim you are making?
So I claim that there are m non-congruent solutions to the equation x to the m is 1 modulo P.
Okay.
Okay?
And what is m?
Hmm?
What is m?
M is some positive integer greater than 1.
Okay.
Well, you could take m equals 1, but that's boring. And I call these solutions the mth roots of unity modulo P. I can take a non-primitive, a primitive root of unity modulo P as well. So the definition is the same as for complex numbers. A number z such that the order of z modulo P is equal to m. And it's not very difficult to see that such a number exists. For example, you can just take some primitive root c modulo P and take z to p, c to the power of p minus 1 over m. And it's easy to see that this works. Okay. Sorry, I'm getting a bit ahead of myself. So note that the solutions to the equation next to them is 1 modulo P are the powers of z. And again, this is analogous to the situation in complex numbers. Okay. And then we note that if we take any integer a modulo P, which is non-zero, then a to the power of p minus 1 over m is a solution to the equation next to them is 1. And as we have noted, the solutions are powers of z. So we write that the power is fp of a.
I think fp of a is dependent on m, right?
Yeah, this depends on m.
So in the definition, shouldn't we put m somewhere?
Yeah, but that overloads the notation a bit. I'll actually be also dropping the subscript p a bit later, but the definition also depends on z. So there is no canonical way to pick a primitive mth root of unity modulo P. So the choice actually affects the value of Fp here, Fp of A. So yeah, it's a bit ambiguous, but that doesn't really matter. Then we note some properties of this definition. So first of all, I'm again getting a bit ahead of myself. So first note that the exponent is uniquely defined modulo M, assuming we have fixed the primitive mth root of unity Z. And then we also note that, sorry, a typo, that an integer modulo P is an mth power if and only if the exponent is 0 modulo M. This is a generalization of Euler's criterion regarding quadratic residues modulo P. And the proof is very similar to the quadratic case.
What is the Grange's theorem in
Uh,
this case?
It just says that a polynomial equation modulo P has at most dec P solutions, assuming P is non-constant, of course. Okay, and then we also note that we have some so because we have defined things a bit differently now, we don't have, in a sense, a multiplicative property, but Fp behaves like a logarithm. So it turns products into sums. I could have defined that the function Fp of A takes values in the primitive mth, in the mth roots of unity. So that would be really the analogy of the Legendre symbol, as the Legendre symbol takes values 1 and -1. But I don't know, I like this definition here a bit more.
What is the other possible definition?
So I could have, instead of writing Z to the power of FPA, I could have just put that we let this expression be GP of A. So this would really be the analogy of the Alexander symbol.
Oh, yeah.
But I find the FP function a bit more convenient, but that's really just a matter of taste. Okay. And I think I'm now ready to state the main result. So
But as we saw, this function depends on this z. So wouldn't the value of all these fp of q1 depend on our choice of z?
I'll explain in a second. So so we take some distinct order primes qi and some m, and we consider the primes p equal to 1 modulo m, and we consider the values of the fp function at these primes qi for each such p, and also for each primitive mth root of unity z. And I'll put that into the subscript.
Like z wouldn't be same, cannot be same for all. Okay, sorry, I misunderstood.
So, yeah, as was mentioned previously, the value of the fp function also depends on the choice of z. I'll give an example in a second. So this is by no means uniquely defined, this sequence. However, do note that independent of the choice of z, we have that a is a mth power modulo p if and only if the value of the function at a is 0 modulo m. So this property does not depend on the choice of z. Okay. But yeah, not the claim is that as p varies and also z varies. So we let z go through all of the primitive mth roots of unity modulo p. So then as p and z vary, this sequence we have here attains all of the possible values infinitely often. Okay, and I'll give you some examples. So by definition, fp of 2 is 1, 2, or 3 modulo 3. Sorry, 0, 1, or 2 modulo 3. Okay. The value 0 corresponds to 2 being a cube modulo P. And if 2 is not a cube modulo P, then for one choice of Z, we have and for the other we have FP of 2 being equal to 2 modulo 3. I'm not sure if this is clear to you why this is so.
Will there be exactly 2 such Z?
Yeah. Because we know that there are two primitive cubic roots of unity in the complex numbers. And again, you could usually think of the analogies in the complex numbers. And if you think of that, then this claim becomes actually quite clear. So
Yeah, got it.
I hope the complex analogy is clear. And then the modulo P situation is basically exactly the same. Okay. Yeah. Yeah. And note that the main result shows that there are infinitely many primes P equal to 1 modulo 3, such that this FP of 2 is not 0 modulo 3, as the result says that we get all of the possible values infinitely often. Okay. And this corresponds to 2 being a cubic non-residue modulo P. Okay, I'm cheating a bit here because I have said that the premise QI should be odd, right? And 2 is not odd. I'll explain in a second why I have restricted to odd primes. But in this particular case, things work out. Okay.
Can you repeat what you said?
So I have restricted to odd primes QI in the main result. So I really couldn't apply the main result in this form because I have said that the primes are odd. But there is another version of the main result which says that in this case we can apply the result. So there is no problem. And then note that the fact that we have considered just primes here is not a problem because by the multiplicativity property of the FP function, we can always decompose the problem into primes and then go back after applying the main result. Okay. And then I'll state, or I'll add into this statement that we actually have an equidistribution result. So not only do we get each possible value of the sequence infinitely often, we actually get each of them asymptotically as often. And yeah, well, that needs a bit of explanation what I actually mean by that, because both P and Z vary, but I think that because of the limited time I have here, I will not explain properly what I mean by that. And it's not actually very important, but this is just to prove the point that, as I mentioned earlier, the heuristics we have are actually quite good. So what I mean by each value being attained asymptotically as often is that, for example, the heuristic we had earlier that 2 is a cube modulo P roughly 1/3 of the time, that should be true. So you should take the formulation of this result so that we obtain the heuristics we talked about earlier on. Okay. Then I'll explain why I have restricted to odd primes in the theorem statement. So what's wrong with 2? Well, in most cases, nothing. So so in the case m equals 3, we can apply the theorem even with one of the primes being equal to 2. But if m is equal to 8, then the result is not true. So the case m is equal to 8 is quite interesting. This is related to a well-known problem. I don't know if any of you have heard of it, but the problem is that we ask, do there exist integers a and k? I'll replace k with m, such that a is an mth power modulo p for any prime p. But a is not globally an mth power, so not an mth power of an integer. There is some Imo's hotList problem where we let p be any positive integer, not only a prime. I don't remember the year, but it's some recent hotList, something like 2012 or something. But to this question, the answer is yes. We take a equal to 16 and m equal to 8. And now okay, so we take the polynomial x to the 8 minus 16 and try to prove that this has a 0 modulo p for any p. So we factorize the polynomial. So first we have the obvious difference of squares, which we apply twice, and then we also use the Sophia-Germain identity. And that's it. So 1 of 2 minus 2 and minus 1 is necessarily a quadratic residue modulo p. If 2 or minus 2 is, then we're obviously done. And if minus 1 is, then we look at the third polynomial here and note that it has a 0 modulo p. And then we're also done. So that covers all of the cases. And why do I bring this up? Well, this means that fp of 16 is always 0 modulo 8 when we take m equal to 8, of course. And since fp of 16 is 4 times fp of 2, this means that fp of 2 is always even. Right. And yeah, that's why the main result is not true in this form if we drop the word odd here. But it turns out that the main result is true in this form if we drop what I'm trying to now explain is that this is the only abstraction for the theorem to hold in general. So this ad hoc construction we gave here is essentially the only surprising thing that arises in this kind of structure on power residues modulo primes. So I should be a bit careful with what the condition is if m is divisible by 8. I think this is correct. Yeah, I think this is correct. So okay, yeah. So if m is not divisible by 8, then we have no issues at all. So for example, for cubic residues, 2 is not any special prime. It behaves like any other prime. But if m is divisible by 8, then this construction shows that we have something weird going on. And then we have to do a slight modification to the statement. And yeah. And now if we go back to the start where we had these questions, 5, 6, 7, 8. Question 5, that's clear, right? We ask if a given integer is necessarily a gate power modulo p infinitely often when we take p equal to 1 modulo k. And that, of course, follows right from the main result. Right? Well, actually, maybe I should give some details. It's not quite trivial. Okay, so question 5. We have some integers a and k. Well, I should be using the integer m I used above. Okay, and I ask if a is an empty power modulo p infinitely often. Answer is yes, and solution So the
By
idea,
multiplicativity, it was not multiplicative, I guess.
excuse me?
I think it was not multiplicative.
Well, yeah, it's not really multiplicativity, but the logarithmic property we had. So the idea is that we prove that for infinite many primes p, all of the primes qi are simultaneously mth powers modulo p. And that of course suffices because the product of mth powers is also an mth power. And we get this result by the main result directly. If some qi is equal to 2, then we have to use the modification I gave here, so that I mean, the prime 2 is not a problem in this problem because we only need that fp of 2 is 0 modulo m, and that works out. Is this clear?
Clear.
Yeah. And of course, question 7 is trivial. We use the exactly same argument. Okay.
But for the case k equal to 2, weren't there some problems?
Excuse me?
Weren't there some problems when the product of 3 of them, like when one would be negative or something like that?
Note that here I ask that all of these integers are mth powers modulo m. So I ask them to, I ask them to be powers and not them to be non-powers. So as in the
could you wait for 1 minute? Just let me see this.
Sorry?
Could you wait for 1 minute? Let me try to understand this.
Yeah, okay.
But what if say A1 is negative?
Is that, oh, good point. Well, that's a good point. Give me a second. Yeah, well, that's a good point. So in the main result, I have considered the behavior of fp at primes. And that, of course, gives, by multiplicativity and the fundamental theorem of arithmetic, the behavior at any positive integers. But for the negative integers, we need to understand the behavior of fp at -1. Well, if m is odd, then -1 is an mth power. Of course, because -1 to the m is -1. If m is Maybe I should also remark that the min result is somehow multiplicative also in the m sense. So note that we have settled the issue for m odd. We only have to consider what happens when m is a power of 2. I'm not going to explain this rigorously, but the case when m is equal to 2, we also understand that quite well. Okay, and really what's going on is that we could add some congruence condition to P, and that wouldn't affect the main result at all. I mean, of course, one still has to be careful with the prime 2 because that's the special prime, but we could add this type of condition, and this helps us because then if P is equal to 1 modulo 2 to the k, then minus 1 is a 2 to the k minus 1 power modulo P.
Why?
For k equals 2, in general, we take some primitive root g raised to the power p minus 1 over 2 to the k, and we note that the 2 to the k minus 1 power of that is minus 1.
What does this prove?
That proves that minus 1 is a 2 to the k minus 1 power modulo p.
But m could be anything. It could be 6 also.
Excuse me?
But what to do if m is equal to 6? Say,
Well, we could still add some congruence condition, but I mean, it would take a bit of time to explain this properly, so I'll not do that here. But
okay.
But well, first of all, we have proven this result for positive integers AI, and that's quite good. And yeah, in the case like if m is 6, then we still add the congruence condition. But yeah, the point is that we can also guarantee, in addition to the primes qi being mth powers modulo p, also guarantee that minus 1 is an mth power modulo p. So we can satisfy all of these conditions simultaneously, even though I have only claimed that we can do it for the primes. Okay. For question 6, For question 6, the answer is yes. In all cases except the very obvious one, where A is a gate power modulo, the gate power of an integer, and also the ad hoc construction where A
Could
is
you
16
show
and K is.
once again what you had written for m equal to 6 case?
For m equal to 6, we restrict to primes P congruent to 1 modulo 12 instead of only 1 modulo 6 as we did previously. Then you can check that the sixth power of g to the power of p minus 1 over 12 is minus 1. So minus 1 is a sixth power modulo p.
Okay.
Okay. And then by the main result, we can also guarantee that the primes qi are empty powers modulo p. So that gives us everything we need. Then we can use the multiplicativity property to get the result for any of our integers ai.
Got it.
And for question 6, you have to be a bit careful because if we take a equal to 2 to the power of 4 times 101, say, and k equal to 8 times 101, then this fails. Of course, this is essentially the same abstraction as we had for a equal to 16 and k equal to 8. But yeah, and for question 8, the answer
Did
is
we prove
not pretty.
Q6?
Mitä? What?
Did we solve Q6?
Essentially, yes, but that would need some details, so I'll not go into that.
Like how, like you have only stated answer or some details also?
Yeah, I'll not be giving a proof, but the idea is again to reduce the problem to the primes and then use the main result and then use multiplicativity to go back.
Okay.
And question 8 is again the same ideas, but that requires a lot of work, and the answer is not pretty. In contrast to the question 4, where we had some nice condition for the system of linear equations to have a solution. But yeah, I have used my time, so I think that's all for today. And I have not even tried to prove the main result because that requires a lot of mathematics from algebraic number theory and Galois theory, but if you want to read more on these topics, then I advertise my work, Polynomial and Exponential Equations Modulo Primes. So you can find the PDF just by Googling this topic, I hope. And then I develop the foundations of algebraic number theory and use those methods to answer exactly these type of questions and some questions on exponential equations modulo primes as well. But well, it's a bit long, so if you're not very interested, then that might not be the shortest way to really answer these questions. But anyways,
Could you all please? Could you also please send this PDF on Discord? So
yeah, well, I can, yeah. Or I can send the link where you can find the PDF file or something. So
yeah, anything is fine.
but yeah, that's all for it today. Thanks for your questions and interest. And if you have any questions later on, then you can send me a message or something.
Yeah, thanks for the lecture.
Thanks.